Look at this real-world failure, 40% to churn in a single week. Why? Because the dev team treated AI like a standard REST API without considering the 3-second round trip time. In production, every millisecond is a potential user lost. When users see a loading spinner for a simple text correction or a basic query, they don't wait, they leave. Beyond the UX, cloud-only paradigms face a brutal economic reality where scaling costs outpace revenue growth. If every user interaction costs you 0.105 in API fees, you aren't building a service. You're building a liability. The 2024 model of cloud-first is officially dead. This isn't just about speed. It's about the very survival of your product's ROI. But wait, is the cloud always the enemy? Not necessarily. The problem lies in how we route the traffic. By the end of this lecture, you will know exactly how to slash those server bills by 90% while making your app feel 5 times faster. The old way was linear. Client asks, server thinks, client waits. The 2026 SLM-First approach flips this entirely. We execute the initial reasoning locally on the device at 20 tokens per second. The user gets immediate, zero latency feedback for 80% of their needs. This is the local first filter. If and only if the local model identifies a high complexity task beyond its parameters, it triggers a cloud escalation in the background. This hybrid flow ensures that only a tiny fraction of your requests hit the expensive GPT-5 or Claude 4 endpoints. This ROI isn't just a theoretical improvement. It's the difference between a profitable, snappy application and a slow, money-burning experiment. But can a mobile phone really handle a sophisticated language model without melting? The hardware transition in the last year might surprise you, and we are diving into those technical numbers right now. Why are we talking about this now in 2026? Because the hardware finally caught up to our ambitions. We have transitioned from running simple image filters to full-blown transformers on silicon. The 2026 standard for flagship devices has reached a staggering 75 TOPS on the MPU. Think about the 19 Pro or the latest Snapdragon chips. They aren't just faster CPUs, they are specialized matrix multiplication machines. In the past, we struggled to run even 1B parameter models without the phone heating up like a toaster. Now, with dedicated 4-bit and 2-bit quantization support in silicon, AB models are becoming the baseline for real-time inference. If you aren't optimizing your app for these MPUs, you're leaving 90% of the device's processing power on the table. But the hardware is only half the story. You need the right weights to fill those transistors. Which models are actually winning the edge war? Let's look at the current leaderboard. The landscape for 2026 is dominated by what I call the small but mighty category. We have the Phi 3 Mini, Llama 3.21b and 3b variants, and the latest Quantini series. These models are meticulously optimized for 4-bit quantization, fitting comfortably within the 2GB to 4GB RAM overhead common on modern mobile devices. They represent the sweet spot for edge AI. These models aren't meant to write your PhD thesis. They are designed for intent classification, text summarization, and local RAG tasks. Choosing the right model for your app depends on your specific task. Summarization might favor Llama, while coding logic might favor Phi. But having a model isn't enough. The real nightmare starts when you realize how limited the NPU memory bandwidth actually is. This is where most developers fail. In the next chapter, we will face the harsh reality of hardware constraints that no one tells you in the marketing slides. In the field, marketing specs are the biggest trap. You'll see chipset manufacturers bragging about 50 TOPS or 80 TOPS for their latest NPUs in 2026. But here is the cold truth from someone who has shipped actual products. TOPS is a theoretical maximum that almost never translates to your application's tokens per second performance. While a high-end mobile chipset might claim massive throughput, your actual SLM might struggle to hit 10 tokens per second due to software overhead and driver inefficiencies. When you're choosing a target device for your SLM-First architecture, look beyond the marketing sheet. You need to benchmark the actual NPU utilization using tools like the Qualcomm AI Stack or Apple's Core ML performance tools. If your model isn't optimized for the specific NPU kernels, it will fall back to the GPU or, even worse, the CPU, causing your inference speed to plummet and your device to overheat instantly. But wait, if TOPS isn't the answer, what about the precision of the model itself? To survive on the edge, we have to talk about quantization. You cannot run a 7B parameter model in FP16 on a standard 2026 smartphone. It will simply crash the app with an out-of-memory error. The industry standard has shifted toward INT4 and even 2-bit quantization for specific tasks. In my experience, moving from FP16 to INT4 reduces the memory footprint by nearly 75%, while only sacrificing a negligible amount of reasoning capability for common tasks. We use techniques like AWDBQ, activation await quantization, or GGUF formats to ensure that the NPU can handle the weights efficiently. If you don't quantize, you are essentially asking for a high-cost cloud bill because your on-device attempt will fail every single time. However, the process isn't just about shrinking. It's about maintaining the intelligence threshold of the SLM. This leads us to a bigger problem. Even if the model is small enough, the data can't get to the processor fast enough. Is the NPU really the bottleneck? Here is the silent killer of edge AI, memory bandwidth. In the field, we often see developers scratching their heads because their NPU usage is only at 30%, yet the inference is slow. Why? Because the NPU is waiting for the memory. LPDDR5 and the upcoming LPDDR6 are fast, but LLMs are autoaggressive. They need to fetch the entire model's weights for every single token they generate. If your model is 2 GB and your bandwidth is 50 GB, you have a theoretical ceiling that you can never exceed, no matter how fast your NPU is. This is why unified memory in chips like Apple's Silicon or the latest high-end Snapdragon units is so critical. You must design your architecture to minimize weight reloading. If you're constantly swapping models in and out of the VRAM, your user experience will be destroyed by latency. But wait until you see what happens when we add vision to the mix. It gets even more complicated. In 2026, the biggest leap in on-device AI isn't just text, it's vision. Vision language models, or VLMs like PalaGemma or Lava Edge, are now small enough to run locally. Imagine an app that does instant OCR or object detection without ever sending a photo to the cloud. From a senior engineer's perspective, this is a massive win for user experience. Local VLMs eliminate the 2-3 second latency of uploading a high-res image to a server. You can process frame by frame on the edge, providing real-time feedback. However, VLMs are heavy on the KV Kakian memory. You need to be extremely disciplined about image resolution and patch sizes. If you feed a 4K image directly into a local VLM, the device will hang. We use pre-processing to downscale and normalize images before they hit the NPU-optimized VLM layers. But why bother with all this complexity if the cloud can do it better? The answer lies in something far more valuable than speed. The absolute strongest argument for the SLM-First approach is privacy and regulatory compliance. When you run a VLM on device, you achieve zero data transfer. In our field, dealing with data processing agreements or DPAs and GDPR can take months of legal back and forth. If the user's data, especially sensitive photos or documents, never leaves the RAM of their device, most of those hurdles simply vanish. There is no risk of a server-side data breach for that specific task. This isn't just about security, it's about trust. By 2026, users will be savvy enough to check if their AI features work offline. If your app requires an internet connection for basic image analysis, you're losing. But remember, on-device isn't a silver bullet. Some tasks are too complex for a 2B or 3B model. How do we decide when to stop struggling locally and call for cloud reinforcement? In the next chapter, we'll build the brain that makes that choice, the escalation router. In the field, we don't just throw every user query at a 7 dB model in the cloud, because your infrastructure bill will explode long before you reach 1 million users. The real secret to a sustainable AI product is the escalation router. Think of it as a triage nurse in an emergency room. The primary goal is local first. We use an extremely lightweight model, often a 0.11b or 0.5b parameter SLM, to perform intent classification. Does the user want to change a system setting? Local. Are they asking to summarize a text they just typed? Local. Are they asking for a deep analysis of global economic trends? That is a clear case for escalation. Most junior developers try to solve this with simple regex or keyword matching, but that is a classic anti-pattern that fails with the nuance of natural language. You need a semantic gatekeeper that understands context without consuming 2 GB of RAM. If this router adds more than 50 amps of overhead, you've already lost the performance game. But how do we actually quantify the hardness of a query for a machine? This is where confidence scores and probability thresholds come into play. Let's look at how we implement this gatekeeper in code. We aren't just looking for a yes or no. We are looking for a logic-based confidence score. In real-world projects, I often use a distilled version of a model like Firequinn to output a specific routing token. If the model is 80% confident it can handle the task, we execute locally. If the entropy is too high, meaning the model is confused, we immediately trigger a background call to the cloud. Notice the threshold variable in the code. In production, this isn't a static number. You tune it based on your current server load and battery levels. If the device is at 5% battery, you might raise the threshold to push more work to the cloud to save local NPU cycles. Conversely, if the user is offline, you force a local fallback regardless of the score. This logic is what separates a toy app from production-grade AI system. But efficiency is only half the battle. If the user has to wait for a local failure and then wait again for the cloud, the UX is ruined. This brings us to the critical concept of the latency budget. In the world of edge AI, double latency is the silent killer. Imagine an SLM takes 1.5 seconds to try and fail, then the cloud takes another 2 seconds to answer. That's 3.5 seconds of a spinning wheel. The user will uninstall your app before the response arrives. To prevent this, we implement a fail-fast mechanism. We set a strict latency budget, say 500 ms for the router. If the router doesn't give a high-confidence local path within that window, we cut it off and start the cloud request in parallel. Sometimes we even fire both requests simultaneously and race them, though that's expensive. In a 2026 production environment, we use speculative execution where the local model starts streaming a placeholder or a thinking UI, while the cloud prepares the heavy lifting. The goal is to ensure the perceived latency is always closer to the local speed, even when the cloud is doing the work. You have to design for the worst-case scenario where both the NPU and the network are struggling. Theoretical logic is one thing, implementation is another. What's the actual technical stack we use to build this hybrid bridge? Building a cross-platform router isn't as simple as writing a Python script. In real-world deployment, you're dealing with a fragmented landscape. For iOS, you're looking at CoreAML. For Android, it's often Executorch or the MediaPipe LLM Inference API. The industry is moving toward unified frameworks like MLC LLM, which allows you to compile models once and run them across Vulkan, Metal, and QDA. But here's the reality check. Hardware abstraction layers are still leaky. You can't just assume an NPU on a mid-range phone will behave like the one in a flagship. You need a stack that includes a hardware capability discovery layer. This layer detects the specific NPU version and available VRAM before the model even loads. If the device is too weak, the router defaults to cloud-only to prevent a system crash. We use GGUF or ONX formats as our common language, but we optimize them into native binary formats during the app's first boot. This stack is what enables this SLM-First dream. But wait, what happens when there's no network at all? How do we build an offline-first AI that doesn't just display a no-internet error? The ultimate test for an escalation router is the offline experience. In an offline-first architecture, we design for graceful degradation. When the cloud is unreachable, the router shouldn't just throw an exception. It should switch the SLM to a self-reliance mode. This involves using a local vector database, like a mobile-optimized Chroma or FACE, to provide context even without a server connection. We also use prompt templating where the SLM is instructed to be more concise and less creative to save battery. In professional settings, we call this the low-fidelity mode. It's like how a video player drops from 4K to 480p when the bandwidth is low. You must manage user expectations through the UI indicating that only basic AI is available offline. This ensures functionality is never truly broken. Now that we have the architectural blueprint for routing and fallback, it's time to see how this design survives the chaos of the real world. In the next chapter, I'll share some brutal battle stories from the edge trenches, where memory leaks and thermal throttling turned our perfect plans into nightmares. You spent weeks optimizing your Llama 3.21b model. On your development workstation, it's lightning fast. But the moment you deploy it to a real-world mobile device, reality hits you hard. After 5 minutes of continuous inference, the device starts burning up, and the NPU or GPU frequency drops by 40%. This is thermal throttling, the silent performance killer in edge AI. In the field, we see users complaining that the app becomes sluggish or the battery drops 1% every minute. We can't just ignore this. We need to implement dynamic compute budgeting. This means monitoring the device state via APIs like Android's Power Manager or iOS's Process Info and proactively scaling down the context window or switching to a smaller model version when the heat rises. Real-world engineering isn't just about the fastest token per second. It's about sustainable performance over a 30-minute session without turning the user's phone into a hand warmer. But wait, what happens when the model is actually running fine, but the results start getting weird over time without you ever knowing? The next scene reveals the difficulty of monitoring what you can't see. In a cloud environment, you have ELK stacks, Datadog, and full visibility into every prompt and response. On the edge, you have total darkness. Due to strict privacy requirements, which is likely why you chose on-device SLM in the first place, you cannot simply log user data to your server. This creates a massive observability gap. How do you know if the model is drifting or if the INT4 quantization is causing specific edge case failures? Experienced teams use privacy-preserving telemetry. Instead of logging the text, we log confidence scores, token latency, and escalation rates. If you see the escalation router triggering the cloud fallback 80% of the time for a specific task, you know your local model is failing. We also use shadow logging where a tiny, random sample of anonymized metadata is sent back for quality auditing. Without these metrics, you are flying blind in the trenches. This leads us to a critical question. What if the model's failure isn't due to the hardware or monitoring, but a fundamental flaw in how we compressed it? Let's talk about the quantization trap. Everyone loves 4-bit quantization because it shrinks an 8GB model to 2GB, making it fit on almost any phone. But here is the trap. INT4 is not just slightly worse than FP16. In many SLMs, the drop in perplexity is nonlinear. You might notice outlier features, specific neurons in the transformer layer that have huge activation values. When you squeeze these into a narrow 4-bit range, they clip, leading to bizarre hallucinations that never appeared during server-side testing. The model might start repeating words or, worse, giving confidently wrong medical or financial advice. We call this quantization-induced hallucination. It's particularly dangerous because it only happens on specific prompts that trigger those clipped weights. If you're seeing your SLM go off the rails in production, don't just blame the model size, blame the weight distribution. But wait, is there a way to keep the 4-bit size while regaining that lost intelligence? There is a specific calibration process we use in the field to fix this, and it doesn't require a supercomputer. To survive the quantization trap, you can't just use a generic conversion tool. You need quantization-aware training or at least a very high-quality calibration step. When we fine-tune models like Llama 3.2 for mobile, we use activation-aware weight quantization or AWQ. This involves running a small representative dataset, maybe 5 to 12 samples of your introduction prompts through the model to see which weights are important. We then protect those weights from being aggressively clipped. This calibration phase is what separates a toy app from a production-grade AI service. In 2026, we are even seeing knowledge distillation, where a large 70B model supervises the 4-bit quantization of a 1B model, essentially teaching it how to behave despite its limited memory. By following a rigorous process of fine-tuning, calibration, and validation, you can achieve 95% of server-grade accuracy at 10% of the cost. Now that we've survived the hardware and model trenches, it's time to put it all together. In the final chapter, I'll give you the exact blueprints and best practices for launching your SLM-First architecture. Moving from a cloud-only prototype to a production-grade SLM-First application is where most teams hit a wall. In the field, I often see developers optimize for benchmarks while ignoring real-world device constraints. Your local model might run fine on a high-end workstation, but on a mid-range smartphone, you'll face thermal throttling and aggressive background process kills. You must verify if your 4-bit quantization, preferably using GGUF or EXL2 formats, actually fits within the target device's available VRAM after the OS takes its share. Another critical anti-pattern is cloud blindness, where the app hangs because the local model failed and there was no immediate fallback trigger. You need a supervisor thread that monitors inference health and switches to the cloud API if the local NPU latency exceeds 2 seconds. Don't ship until you've tested the battery drain under sustained 10-minute inference sessions. If it drops 5% in that time, your quantization or context window management is failing. This checklist is your shield against the most common production disasters. But how much money are we actually saving by doing all this extra work? Let's look at the hard numbers next. Let's talk about the bottom line, because at the end of the day, your CFO cares about the bill. Running a flagship model like GPT-4 for every single user greeting or basic data formatting task is simply financial suicide at scale. In a typical 2026 service architecture, we've observed that roughly 85 to 90% of user intents are repetitive or low-complexity tasks. By routing these to an on-device SLM, you are not just saving on token costs, you are eliminating the hidden costs of serverless cold starts, load balancer overhead, and cross-region data transfer fees. Look at this comparison table. For a service with 1 million active users, the cloud-only approach can easily burn 6 figures monthly, with a 90% local routing strategy that cost collapses by nearly 20 times. Plus, you gain privacy by design as a marketing advantage because the most sensitive data never leaves the user's pocket. This isn't just a technical choice, it's a fundamental shift in business sustainability. This looks great for today's hardware, but what happens when the mobile chips double in power next year? Let's look at how to future-proof this. As we look toward 2027, the line between edge and cloud will blur even further. The hardware leaps we are seeing in NPUs mean that on-device multimodal will become the standard, not the exception. Your architecture must be ready to handle not just text, but local image and audio processing simultaneously. This requires a shift from static model deployment to a model registry pattern, where the app dynamically fetches the most optimized weights for the specific chipset it detects, be it a Snapdragon, MediaTek, or Apple Silicon. Stop hard-coding paths and start building abstractions. The future belongs to hybrid intelligence, where the cloud acts as the long-term memory and deep reasoning engine, while the device handles the real-time interaction. You've now seen the secret to killing AI server costs without sacrificing performance. This concludes our series on SLM-First architecture. Now take these blueprints and start building applications that are not only smarter but also faster, cheaper, and more private than anything that came before.